Happy Friday the 13th, everyone. So let's get started. So last time we were talking about the linear model, and basically we have a picture here which sort of illustrates what we want to do. We have a bunch of data points. Each data point has a predictor value and a target value, and we would like to essentially model the trend of the data as linear, which means that we're postulating that there's some line that goes through the data that is a pretty good fit to most of the data. So we model this as follows. We're always going to use X for the feature or the thing we're using for prediction, Y for the target, the thing we're trying to predict, and then we have these two parameters in our model. Beta 0 is the intercept on the vertical axis of that line, and then beta 1 controls the slope of the line. And we also, when we state it this way, we use an approximation to remind ourselves that the data doesn't necessarily fit perfectly on that line. But to be a little bit more explicit, we can add in epsilon, which is what we call the residual or the error, and then write this with an equality. And now this error measures the distance from a given data point to that line. And then in order to fit that model to the data, we decided that we're going to try to minimize the sum of squared errors or sum of squared residuals. So that's our objective here. And that gives us sort of a tractable problem that we can attack using mathematics. And so as a first step towards that, we started talking about some classical statistics, because what we'll see today is that if we compute these various statistics for our data set, then the optimal beta 0 and beta 1 are just some very simple functions of those statistics. So that's what we're going to do today. So just let's remind ourselves, we talked about the sample mean. So we have the sample mean of X, the features, sample mean of Y, the targets. We also talked about the sample variance, which is like the average squared distance around the sample mean. We have the sample variance of X and Y. And then we also talked about the sample covariance. The covariance gives us a notion of how related these two quantities are, X and Y. And we said that if we normalize this sample covariance by dividing it by the sample standard deviations of X and Y, we get this thing we call the correlation coefficient. And what's nice about that is that the correlation coefficient is always between 1 and -1, and therefore it's not influenced by the absolute size of the X and Y, and it's a lot more interpretable. And as we'll see, this correlation coefficient gives us a direct measurement of how successful we're going to be at linear prediction or linear regression. So we'll see that later today. And then just sort of in preparation for some of our derivations that we're going to do today, as well as throughout the semester, we derived some useful relationships here. So if you have, let's say, some quantities xi, and you're looking at the average squared value of xi, that turns out to be the sample variance plus the squared sample mean. And then we have a similar one for this cross statistic between X and Y. So if you're looking at the average product of xi, yi, that's going to be your cross covariance plus the product of the sample means. So we'll see why those are useful in just a little bit. Okay, any questions so far and anything you did last time? Okay, so all right, so the approach we're going to use to do our derivation of the parameter values beta 0 and beta 1 that minimize RSS is going to use the concept of the gradient. And this is an important concept we're going to see many times throughout the semester. So we're just seeing it for the first time today. We don't have to understand everything about it today. We just want to understand mainly one or maybe a couple of basic things. Number one, how is the gradient defined? And number two, what's special about the gradient that helps us minimize the RSS? Okay, so the way that the gradient is defined is that if you have some function, in this case it's RSS, function of multiple variables, in this case beta 0 and beta 1, the gradient is a vector where each term of the gradient is a partial derivative with respect to one of those parameters. So in this case, we just have two parameters. So our vector is 2 by 1, and the first coefficient is drss d beta naught, and the second is drss d beta 1. Okay, so that's how gradient is defined. Now, the reason why the gradient is useful is we can understand that better if we have an interpretation of the gradient. So here's an interpretation of the gradient. Imagine that you have, so we can think of this function as like a surface. So here I'm plotting the value of RSS on this z-axis versus, let's say, beta 0, beta 0 and beta 1. And so as I move this little vector beta around, as I move that around, I get some point in that horizontal plane. That leads me to a value of this function. Okay, so imagine that you are sitting somewhere on that surface. If you look for the direction that is pointing steepest uphill, that has the same direction as the gradient vector. Okay. Number two, if you look at the slope, in other words, how steep it's pointing uphill, that has the norm of the gradient vector. So the gradient vector tells you two things. It tells you, number one, what's the direction of maximum slope, as well as what is the slope there. Okay. Here's another picture of that surface where the gradient is at every one of these points. It's plotted using a little arrow. So the direction of that arrow shows you the direction of the gradient, and then the length of the arrow is representing the norm of the gradient. And so this surface, this is a quadratic surface. What that means is as you get farther away from the minimum, it gets steeper and steeper. Right? So you can see the gradient lines getting larger and larger as you go farther away. And that makes sense. This is what we call a paraboloid, which is just a multidimensional extension of a parabola. It's just a parabola simultaneously in the different dimensions. Okay, so what is special about the gradient that helps us minimize the function? Does anybody have any ideas? So when you look at this picture, where's the minimum?
Right in the center.
Right in the center, yeah. And what's special about the gradient right in the center?
It's zero.
It's zero, exactly. Because the idea is if you really are sitting at the minimum point, any direction you look in, there's no slope, right? When you're right at the middle, right at that minimum, there's no slope in any direction. As soon as you get off the minimum, then there starts to be a slope up in some direction. Okay, so that's essentially the whole idea. Is and it's a little bit more complicated. We don't need to understand all the technical details right now, but let's just focus on that idea. We want to find the point with zero slope. It's definitely going to work for this quadratic function. And like I said, we're going to talk more about this in later units, and we're going to get more technical, et cetera, et cetera. But right now, that's the main idea. Now, let me just highlight it here. The zero gradient point is guaranteed to be a minimum of this function that we want to minimize. Okay. So our whole approach is just going to be to try to figure out which beta is the zero gradient beta, and that's going to be the RSS minimizing beta. Okay. Is that idea clear? Any questions on that? Okay, so what we're going to do in the next few slides is we're going to derive these expressions. I'm just going to write them down right now. So for beta 1, we're going to see that the optimum is the cross the cross correlation or cross covariance over the variance of x, or we can also write it as the correlation coefficient rho xy times sy divided by sx, and beta 0, the intercept is going to be y bar minus beta 1 x bar. Okay, so you can see that you can summarize this data set, all these xi, yi pairs, all down to just a few simple statistics. Basically, you could say these two and these two. If you know those, then that's all you need to know to figure out what the RSS minimizing beta 1 and beta 0 are. So that's kind of why we define them. They're going to help us derive it, and they actually give us a lot of intuition, as we'll see later. Okay, so how do we get there? So we're going to, like I said, we're going to zero the gradient. That's our main approach, and we're actually going to use this approach all throughout the semester, figuring out how to zero that gradient. So, so essentially we need to find the values beta 0 and beta 1 that jointly satisfy these two equations. Each of these partial derivatives should be 0. Okay, so let's start by deriving what those partial derivatives are. So we're going to have, in other words, I just need to plug in the RSS at this point. So my RSS equation, I'll just write it out. So remember, it's going to be, it's the square difference, the sum of the square differences between the true targets yi and the approximation, our predictions y hat I. Let's plug in the expression for y hat I, in this case minus y hat I. It's going to be minus beta 0 minus beta 1 xi, right? That's just plugging in our y hat into our RSS expression. So now we have a little bit of calculus to do. So, and calculus is going to be another theme of machine learning. It's stuff that I think you guys know better than linear algebra, so I haven't really been stressing on a review, and we'll be doing a lot of it as we go through the course. But so how do we do this partial derivative? The first thing to remember is that differentiation is linear. It's a linear operation. That means that you can move it through summations and you can move it through scalings. So we can essentially move this guy through the sum and say that we're going to have the sum of the partial derivatives of this thing. That's what I mean by moving through the sum. Okay, so now let's focus on what is the partial derivative of this quadratic. How do we attack this? Does anybody remember there's sort of a key word?
Variable change?
No, we don't need to do anything so complicated. Chain rule, exactly. So, so basically, you probably remember how this goes, but for this quadratic, it's going to be 2 times the derivative of this with respect to beta 0, right? Or sorry, 2 times this times the derivative of that with respect to beta 0. So let's write the 2, we'll put the 2 in front, and we'll write the inside. And then finally, we have to write the derivative of this with respect to beta 0. And what is that? Minus 1, because of that minus sign. So we'll also put the minus in front. Okay? Everybody good with what we just did? Okay. Well, we'll get to do it again. Get to see another example. So, so let's do it for the second equation. So now we have d beta 1. We have the same RSS expression as above. And so we have the same chain rule approach. So we need to take the partial derivative of this quadratic with respect to beta 1. And that's going to be 2 times this interior part times the gradient of this with respect to beta 1. So let's write all the simple stuff first, just like we did above. Okay, and then the last thing is what is the gradient of this inner term with respect to beta 1? Minus xi. Exactly. So we can put the minus in front. We can't put the xi in front, right, because we're doing a sum over I. So this xi is going to stay out there. Okay. All right, so is everybody good with that? Okay, so yeah, so I'm not expecting you to write out everything because there's, maybe too much to write out to make it worthwhile. So I just kind of filled in a lot of these blanks. But what we're going to do next is we're going to multiply both sides of these equations by minus 1 over 2n. And notice that the left side of the equation is 0. So multiplying that doesn't change anything. And this multiplication in here is done to get rid of the minus, get rid of the 2, just to make it more pretty, and then to put in a 1 over n there. And why do you think we might be putting in a 1 over n there? Right, because we want to relate it to those statistics, and they had the 1 over n. Okay, so when we do this with the first one, multiply this by minus 1 over 2n, we get 0 equals 1 over n, and then we have what remains from that sum. And now let's kind of apply this averaging operation to each one in turn. So we have the average of yi, this first term. We recognize that as y bar, the sample mean. Then we have the average of minus beta 0, which is just minus beta 0. And finally, we have the average of this last term. We can pull out the minus beta 1 out of that average, and then we have the average of the xi's, which we recognize as x bar. So just sort of summarizing what we figured out, we have 0 equals y bar minus beta 0 minus beta 1 x bar. We can just rearrange that a little bit to find out that beta 0 equals y bar minus beta 1 x bar. Okay? So that is our first equation from the previous slide that we've now derived. Okay, any questions on this first one? Okay, so we're going to do the same thing with the second equation. That's going to give us 0 equals 1 over n times this sum. And here I happen to write the xi in front of that bracketed expression. But we can do the same approach, or we split this into 3 separate sums. So we're going to have the sum over, or the average of xi, yi. Then we're going to have the average of xi times minus beta 0. And finally, we have minus beta 1 times the average of xi. Oh, actually, this is where we're going to get an xi squared. Okay. So, and here is where we encounter these terms that we've seen before, right? These are exactly the terms we said that show up pretty often in derivations, and those are the ones that we related to the simple statistics back on this page. So now you can see why we did that. And this happens in many other derivations, not just this one. Okay, so we're in a position to move on. Is everybody good with this? All right. So now we're going to plug equation 3 into equation 4. I'm going to basically replace that beta 0 with y bar minus beta 1x. And as you can see, that's going to give us an x bar times y bar, and it's going to give us an x bar squared minus beta 1. So here's the x bar squared minus beta 1 term, and then this last term here is there. And so now, maybe this looks even more familiar. So what was this exactly? What did we derive this to be? You remember? It was SXY plus X bar Y bar. And now we're removing the X bar Y bar. And so we're left with just SXY. Exactly. Okay, similarly, we have this, right? This guy was sx squared plus x bar squared. So now we remove the x bar squared, and we have just sx squared, or we can call it sxx, same thing. And so now you can see we have that expression for beta 1. We just rearrange, and we find that beta 1 is sxy divided by sxx. Okay. Okay, so we found the coefficients we were looking for. We might also want to know not just the coefficients, but how well this worked. So let's compute the RSS. Let's derive an expression for the RSS itself by plugging in those optimal parameters. So again, RSS, we defined it like this. So now let's plug in the expression for beta 0. That's going to give us y bar minus beta 1 x bar. And I've grouped the y bar with the y and the x bar with the x here. And then we have a quadratic, right? So a difference of two terms squared. Let's expand that into the first squared, the cross terms, which is this, and the second squared. We get a beta 1 squared, and we get this stuff squared. So does this first sum look familiar to you? Yeah, almost the variance. There's one other thing. The normalization is not included here. We don't have the 1 over n. So this is going to be n times the variance of y. Oops. S, y, y. And what about this next one? Yeah, n times sxy. And finally, n times sxx. Okay, so now we're almost done. We just need to rearrange a little bit. So there's a common n everywhere. So we can pull that out. And then we have syy. Actually, we can also do this. We can plug in this expression for beta 1. And so that's going to give us, we have this sxy, and we have another one. So we have sxy squared. And then this guy, division by sxx, shows up there. And finally, well, let's see, am I missing? Oh, yeah. And then finally, we're going to plug this into here. So that's going to get squared. So we're going to have sxy squared, which is here, sxx squared in the denominator, but then that's multiplied by sxx. So we have sxx in the denominator. And now you can see that actually these terms are the same. It's just you have minus 2 times it and then plus it. So that simplifies to this. And we're almost done. To make it a little bit more interpretable, let's pull out a factor of syy out here. And then we have this. Does this look familiar?
The coefficient?
Yeah. Is this correlation coefficient, or is it slightly different?
Square.
Squared. Correlation coefficient squared. That's exactly it. So we have n times 1 minus rho xy squared times syy. Okay, so we finally have an expression for the actual RSS that we get. All right, any questions on the derivation?
This is the minimum RSS, right?
Yeah, this is the minimum possible RSS that can be obtained because we plugged in the RSS minimizing coefficients. Exactly. It's the minimum value. Okay.
But this is still dependent on like and the variance of y.
Exactly. That's a great point. We're going to return to that point in just a moment. That's a great observation. Okay, but for the moment, let's just go back to our automobile demo and apply the equations that we've derived to see what happens. So here was the data, we're trying to predict miles per gallon from horsepower. We have this data here. Even though it doesn't look perfectly linear, we're still applying our linear model just because it's simple. We know how to do it. So the code, as you can see, is pretty straightforward. We compute the sample means of the feature and the target. We compute the sample covariances of the feature and the target and the sample cross covariance. And now that we have those, we know that beta 1 is just that simple ratio, beta 0 is that simple equation. We'll talk about R squared in a moment, but from the beta 0 and beta 1, we can plot our line, and we see that that's the fit we get, which visually looks pretty good, right? I don't know, certainly doesn't look off. It looks like a pretty good fit. So that's, just a simple application of this idea to our miles per gallon prediction problem. If you want to see another similar little tutorial, this is a pretty good one. Okay, any questions so far? Okay. So let's now return to this question about understanding goodness of fit. Like, how successful were we in our prediction? So when we look at the picture, we see that it's definitely not perfect, but, how do I describe this? Like, can I come up with a quantitative evaluation of how good this is exactly, a single number? That's our objective. So the RSS, the minimum RSS that we derived, has sort of two issues with it that were just noted by an attentive student. So one issue is that it's dependent on n. So the more data I'm fitting, the larger the RSS gets, which seems kind of unfair because often more data is better. The second issue with it is that the more variance there is in the targets, the larger the RSS gets. So, if I take the same problem, let's say, and I just double everything, it's equivalently the same problem, you would see that the RSS goes up by a factor of 4, right? So it seems like maybe this is a little distracting. Maybe that's not really telling us something super useful. So that's the idea, is we want to use a normalized version of RSS. And in particular, we want to remove the dependence of n by dividing by n. We also want to remove the variance of y. And now this thing is useful because this thing, this is sort of a metric that's independent of data size, independent of the exact scaling of the targets. And we could use this, but it turns out that most people use something that's just a little bit different than this, basically just 1 minus that quantity. 1 minus the RSS over n divided by sy squared. So this is called the R squared coefficient of determination. Okay. So there's sort of a story about, what does this mean, coefficient of determination? And if you're curious, you can click on the Wikipedia link. You can look at that story of it. It's not going to be important for this class because I think it's enough for you guys to understand that R squared is like 1 minus a normalized RSS, and also to understand some special cases. So so the first thing you notice is that we obviously want to make RSS small, right? So that means that this thing, the larger this is, the better. Right? So what's the largest that we can ever get? 1, because the smallest RSS can ever get is 0. Okay, so when we have R squared equals 1, we have perfect prediction. So y hat I equals yi for every I. Okay, what about this value R squared equals 0? So obviously this is not something that we hope happens, but in some sense it's, okay. So there's a couple ways to understand it. So let's first of all, one way to understand it is this. Let's remember this is the expression that we derived for RSS. So if I use the optimal RSS minimizing predictor, what's the worst thing that can happen? Like, what is the worst RSS I could get?
1 or n sy squared.
Yeah, so basically, okay, what's the worst value of the correlation coefficient? 0, right? That's when they're totally uncorrelated. So in that case, RSS is n times s squared y, which means that this guy is 1, which means that r squared is 0, right? So r squared is 0 is something that can happen. It's like the worst case. It's the hardest problem when you apply the optimal method. So that means that if you apply the optimal method, you would never, ever get r squared negative, right? If you saw r squared negative and you were applying the optimal method, you would know there's a mistake in your code. Okay. That doesn't mean that it's impossible to come up with some method that gives you negative r squared, right? Certainly you can dream up a very bad method and it can certainly get negative r squared. It's just that it's not going to be the optimal method. And in fact, you can argue that a trivial method also gives you r squared equals 0. And what I mean by the trivial one is the whole idea behind prediction is you collect x's and y's and you use knowledge of x's to get y, right? What if you just completely ignore the x's and you just do the best thing with the y's alone? What would you do? So someone gives you a bunch of y's and asks you to predict y. What would your prediction be?
Just the mean.
The mean, exactly. So I would say a trivial predictor is one that ignores s but intelligently uses y, just sets y hat equal to y bar. That predictor would also get r squared equals 0. Okay, so there's basically, you could say there's two of them. There's the trivial predictor, gives you r squared equals 0. The optimal predictor in the worst case gives you r squared equals 0. And then if you ever see negative r squared, it means it's worse than trivial and certainly not optimal. Okay, so those are the main things we want to understand is these meanings of r squared. Okay, so one last thing is if we plug this expression down here into our r squared formula, we find that r squared is nothing more than rho xy squared. So I think it was last lecture someone asked, like, does rho xy tell us something about the goodness of fit? Yes, it tells us exactly. Rho xy squared tells us r squared. So yes, that's everything in terms of goodness of fit. Okay, good. Any questions so far? All right, so just visually, it's sort of interesting to look at some different rho xy's for just some example data sets. We saw one of these pictures before, but we didn't see all of them. So, okay, so we have some blanks to fill in. So basically, again, a very good fit is when rho xy squared is approximately what? 1. Okay. As that gets close to 1, very good fit. Very poor fit is rho xy 0. Okay. So here is the picture we saw before. A few examples of data sets where you go from rho xy 1 down to 0 down to -1. And so this is the worst case, and the edges are the best cases. Okay. We also talked about this. These are different examples of rho xy that are equal to 1, rho xy that are equal to -1. There's actually a mistake on the slide. Please erase this little 0 here. That shouldn't be there. We also said that if you have a data set that is fitting perfectly on a horizontal line, actually rho xy, you'd get a 0 over 0, and so it's not defined. That's why there's nothing written here. But maybe the most interesting is this row of pictures. These are all examples of how you could get rho xy equals 0. So we said this is one example, but there's actually a lot more examples of data that is maybe predictable in some sense, but it's not linearly predictable, right? Like, for example, like this one. If I told you x was this value, you would say, okay, then y is probably either close to here or close to here. You don't know which one, but at least you can narrow down the possibilities quite a lot, right? That would be an example of a nonlinear predictor. A linear predictor would just throw up its hands. Couldn't really use that data at all. So all these are examples of data sets which you can do some prediction if you do something nonlinearly, but if you do something linearly, you're in trouble. All right. Any questions on this? All right, almost done.
There's
Yep.
still a blank in the third line.
Oh, yes, thank you. One more blank to fill. Okay, so we can also say something about the sign of the slope coefficient beta 1. It must match the sign of the normalized covariance, right? Or this, correlation coefficient. And that's because SXY is positive, SX is positive, so therefore whatever sign rho xy has is inherited by beta 1. Okay, so just knowing the sign, or kind of knowing this, knowing the trend in your data, whether it's like a positive trend or a negative trend, that tells you the slope on beta 1. Okay. All right, so now, even though linear regression seems to be really primitive and overly simplified, it actually can be a lot more powerful if you allow pre-processing of the data. So here's an example. We've been working with this horsepower data to predict miles per gallon, and we acknowledged that this is not really, this data set does not look like it fits well with a linear model. But an interesting or simple thing we can do is what if you inverted, instead of trying to predict miles per gallon, you said, let me predict inverse miles per gallon. You just change the problem. What's interesting is, and you plot that data, now it looks like this. And now you can see it's very close to a linear trend. So this just shows you that if you allow yourself to do some sort of pre-processing your data, then actually linear models might be a very good thing to use. And if you do the fit in this domain, and then you warp that back and plot it in this domain, you end up getting this line. So basically, so you're doing linear modeling with that data, but then you plot that back with the original data, and you get a nonlinear model. Okay. So it's sort of an interesting approach. And what's especially interesting about it is we'll eventually see when we get to neural networks that this is exactly what neural networks do. At the end of the day, they're all doing something linear. But all the other stuff they're doing, all the magic, is pre-processing the data so that that linear stage can work really well. Okay, so we'll see that as we go, but this sort of pre-processing idea is going to be super important as we go through the course. So just kind of keep it in the back of your mind that it's always there as a possibility. What's probably the most tricky thing is if someone just gives you a bunch of data, it's not really clear what sort of pre-processing you can do. That's the hard part, right? Somehow maybe we just had some intuition that we should apply an inverse to our miles per gallon, and all of a sudden we get this nice picture. But that's in general hard to do. I give you a giant data set that's very complicated. It's not really clear what to do. Okay. All right, so that's actually it for this unit. Any last questions? Okay, great. So we can move on then to Unit 2. Unit 2 is extremely similar in spirit to what we did. The difference will be that we're going to use multiple predictors, multiple features. That's the difference. And we're going to basically rederive everything for multiple features. And obviously that's going to be a lot more powerful in terms of being able to do our prediction. Okay, so our data set for this unit is going to be a diabetes data set. So diabetes is a disease that affects hundreds of millions of people. Every year it kills millions of people. So it's an important disease to study. And for example, you might wonder, can you predict the progression of the disease from biometrics like age, sex, body mass index, blood pressure, and various other things that you can get from a blood test? That's sort of an important question, right? And that's exactly what we're going to try to do. So we're going to use this famous diabetes data set. This data set has 442 samples, so it's pretty small data set as data sets go, but it's nice for using in a classroom setting. And it has 10 features. Now notice here they call them attributes or predictive values. So that's, again, it's important to kind of know these different terms. But those are our features. And then the target is given in a separate column of the data set, and it's a quantitative measure of the disease progression 1 year after the measurements are taken. And here are the attributes or the features: age in years, sex, body mass index, blood pressure, and then you can see 6 different things that you can get from a blood test, things like blood sugar level. Okay, so that's the data set. So it turns out that this data set is very easy to obtain because it's built in. And what it's built into is the most important package for machine learning in Python. This is for, let's say, for classical machine learning, not for deep networks, but for anything classical machine learning, it's scikit-learn. It's always in scikit-learn. So it has tons and tons of methods, as well as a few built-in data sets, and we're going to use this extensively. So here's where we import it, and we're going to actually import various sub-libraries, data sets, linear model, pre-processing. So once we get the data sets, you can see it's very easy to get the data. You just do data sets load diabetes. And that's going to give us this data structure that has the feature data as well as the target. And we can pull those out. This is going to be, X is going to be a matrix. We'll talk about that in a second. Y is going to be a vector. And so here we can see the dimensions of the matrix. This is a NumPy thing. If you do dot shape, it basically gives you the dimensions. It can be the dimensions of a vector, a matrix. And so in this case, we see that there's 442 rows in the matrix, and those are going to be the samples in our data set, just like we saw in that pandas data frame. And the number of attributes will be the columns of this matrix. And there's 10 of them. Okay. So let's now talk about a little bit more about how we represent the data with matrices and vectors. So this is going to be what we do all throughout the whole semester. So we're going to have a feature matrix. We're going to call it capital X, a target vector, Y. So as always, I'm using boldface, uppercase for matrices, boldface, lowercase for vectors. Another important thing is that whenever you see a vector, you know, if there's no transpose on it, you know this is going to be a column vector. So anytime there's a row vector, you're going to see an explicit transpose in the notation. And that just makes it easy to see what you're working with. So you don't have to guess what you're working with. Otherwise, it's really hard to know. Okay, so the feature matrix is going to have dimensions n by d. So as we saw last time, n is always going to be the number of samples in our data set. And now this is a new thing. D is going to be the number of features, the number of predictors we're going to use. So here's this X matrix. As you can see, it has n different rows, d different columns. If we want to think about each row as a time, we can call it, like the first row, we can call it x1 transpose, the nth row, xn transpose. If we want to look inside the ith row, we can see all those things here. So we're going to have xi1, which is the first predictor for the ith data sample, xid, the dth predictor, ith data sample. And then similarly, we have our target feature y. as you can see, this is going to be a column vector of dimension n. These are just our different target values for the different samples. So the samples are officially these pairs xi, yi. And the target vector is n by 1. Okay, everybody good with those definitions? Okay. All right, so let's start with the multivariable linear model. So again, in spirit, this is exactly what we did last time. The difference now is instead of a single variable x, we have d different variables that we're using for prediction. So what is my linear model going to be? How do I write it? What do you think? Any ideas? Again, very similar to what we did before. Just use your intuition.
It's going to be like a constant, like beta 0.
Beta
plus
0. Mm-hmm.
Beta, I guess, like I times all the different, like each of the features can have a separate
The
beta
vector.
coefficient.
Yeah, so we'll just, we can write it as a vector, but for now we'll just write it like this. Beta 1 times x1 plus beta 2 times x2 plus ... up to beta d times xd, right? So yes, it's exactly what we did, but now we have a separate slope for each of our different features. And this is an approximate relation, right? Acknowledging that the data doesn't perfectly fit our model. But of course, it is useful to give our prediction a name. We'll call this prediction y hat. So y hat is our linear prediction of y from x. X, the vector, the boldface x, right? That's all the features together. Okay, so the main question that we want to answer in this unit is how do we choose this vector of prediction coefficients, our boldface beta, given our data n pairs of xi, yi? That's the question. Okay, any questions so far on this slide? Okay. Okay, so as we saw on the last slide, y hat is this intercept plus a coefficient times each of our predictors. And in this equation, we're just adding the i's. So here we're sort of talking about what happens in general for our model, whereas here we're talking about what happens specifically with the data we collected because we have these subscript i's. Another way to think about this, if you like, is this is the model that you would use once you've determined all your betas and someone gives you a new x vector that you've never seen before and asks you to do the prediction on that, that would be exactly this equation, right? So this would be your new one that you've never seen, you didn't use for training. But the ones we use for training, that's these. So what we need to do, or what we want to do right now, is we want to come up with a matrix vector model for these predictions because as we'll see, it's a lot easier to work with matrices and vectors than it is with summations and double sums and so on. So what we want to do is write an equation for y hat. Now this is going to be the vector of y hats using our vector of betas. And I'm constructing a new matrix A that, as you can see, it contains all of the features. So this is that, this is our X matrix that we saw previous page. But I've appended a column of ones. Does anybody see maybe why I did this, or how can we write this equation for y hat in terms of A and beta so that this happens for all I?
A beta.
Yeah, it's as simple as this, A times beta. So is that clear? Let's just take a look. This is kind of using all these homework 0 ideas. So if I want to look at, for example, the ith row of y hat, that would be y hat I. I know that y hat I has this equation here. So what I want to do is I want to extract one of these rows and do the inner product with this vector. And now you can see that the 1 that's in the first position will multiply the beta 0 to give me this term, and then all these feature values will multiply against the remaining betas to give that. So by adding this column, we were able to easily handle the beta 0. It's almost like there's an additional feature that we added that always has the value 1. If we didn't have that, what would happen? Yeah. Right. Do you see? Well, let's see. We don't have any pictures here, but can you kind of visualize the problem with forcing beta 0 equals 0? It's like your linear regression has to go through the origin. You might not want it to go through the origin. You might want it to be above or below. Okay. So that's why we have this beta 0. That's why we insert this column. Okay. So now we have a very compact way of writing our predictions. And what if I want to write for a new feature vector the prediction y hat? How could I do that using, we're looking for an expression that involves x and other things on this page. So somebody gives me x. Let's say that I have the beta vector. How can I write this y hat?
X transpose times beta.
Okay, so someone said x transpose times beta. Does everybody agree?
But we have to append a 1.
Yes. Need to append in 1 because actually x transpose has d entries, but beta has d plus 1. So what we actually need to do is append to 1. And that's for the same reason we have that 1's column in the A matrix. We need the 1 when we finally do this prediction. Okay. So here I have a row vector of dimension d plus 1. Here I have a column vector of dimension d plus 1. So when I do this, I get a scalar, a 1 by 1. So, everybody good so far? Okay. Okay, so let's now move on to how do we do our data fit? So this is the equation we've seen previously. This is what happens at the ith sample. We have all our predictors, we have our coefficients, and we have our estimated targets. And we want those estimated targets to match the true ones as close as possible. So what we're going to do is essentially use the same approach as before. How do you think we would write it now? Is it any different? If I want to write an equation for RSS in terms of y hat and y, what would it be?
Summation of the square difference.
Sum over I of the squared difference, exactly. Okay, so it's no different than what we did before. What's different is that the yi itself involves more coefficients. And before we had a picture, which was just a regression line. Now, we don't have a line anymore. We have a plane, or what we call a hyperplane. This is the special case of d equals 2 shown in the picture, where along one axis, maybe I have feature x1, another one feature x2. And by the 1 and 2, I'm not talking about the sample index, I'm talking about the feature index. So, so each one of our points in this case is like a combination of x1, x2, and y. And the thing we're building is a plane. So we have, as before, we have a y-axis intercept, which will still be beta 0. But then we have a slope coefficient we actually have two slope coefficients, right? We have a beta 1, tells us the slope in one direction, and a beta 2 that tells us the slope in the other direction. We get this plane. Any questions on that? The same thing happens when you have more than two features. It's just difficult to draw it because we humans don't visualize well in 4 dimensions. But geometrically, everything works the same, and so it's enough to visualize things in 2 dimensions like this because all the intuitions carry over to higher dimensions. at least until you get to infinity, and then it's a problem. But at least for any finite dimension, everything is fine. Okay, so as before, this is our RSS, or sum of squared errors, sum of squared residuals. On the left side, we have beta. On the right side, the beta is sort of implicitly here inside the y hat I. And as before, these errors, these y hat I minus yi, they are visualized by these little lines. And we want to minimize the sum of the squared line lengths. So you can imagine moving this plane around until the sum of those squared line lengths is minimized. Sum of squared, yeah, is minimized, right? Just move it around. And of course, we're not going to do this by hand. We're going to derive an expression for what exactly those betas are from our data. Okay, so we'll do that next time. This is a good point to stop. Any last questions? Okay, so we don't have class Monday, so have a good long weekend. And see you guys next Wednesday. So there will be a lab. I don't know if the lab's been assigned yet, but Kai-Ying said she would post it either today or tomorrow. And there's going to be a new homework that will go live at 6 p.m. and a new quiz on Unit 1 that will go live at 6 p.m. All that stuff will be due next Friday.